Rojas, and I am your first presenter in the birth of calculus. We will first start with a table of content. First, introduction. Who is Leonardo Euler? Number 2, Euler mathematical notation. And number 3, we will go into determine and discuss what Euler's contributions in the birth of calculus. Logic is a foundation of certainty of all knowledge we acquire. Euler. From it, malalaman natin na ang logic daw ay isang foundation para makakuha tayo ng mga lamang learnings. Kasi sa pagiging logic natin or pagkakaroon ng logic thinking, nauuwanaan natin ang mga bagay-bagay. The next slide is Leonardo Euler. As you can see, those are the images of Euler. This is how he looked. Leonardo Euler was born on April 15, 1707 in Basel, Switzerland. He is a pure Swiss, and his father is a pastor in a church, and his mother is a pastor's daughter. So he really wanted to become pastor like his dad when he was a child, but in the meanwhile, he felt like his heart is connected to mathematics, so he decided to pursue mathematics. He was died on September 18, 1783 by a brain hemorrhage. May I ask from the class, who is Leonardo Euler? Yes, she is a Swiss mathematician and physicist. She is also a preeminent mathematician of 18th century. He's one of the greatest mathematicians that ever lived. His contribution was well recognized and well defined in different forms of mathematics, specifically in calculus, number theory, geometry, trigonometry, and so on. Leonardo Euler education. He studied at University of Basel. He took Master of Philosophy at the age of 16, and later on he published a first formal mathematical paper at the age of 19. Yes, he started too young in mathematics, that's why he had a lot of contributions into it. But first, we're going to talk about his contributions in mathematics and physics. Calculus operation, including its most well-known result, the Euler language equation, has something to do with the field of mathematics and engineering. It is because he studied this he studied the relations of prime numbers and the equation that has a relation. In fact, he's the only mathematician who have two number names. First, the italic e, or also known as the natural base of logarithm, that is equal or approximately equal to 2.71828, and that 2.71828 is an irrational number by the characteristic of it's not repeating and it's infinite. Second, the Euler imaginary constant, or gamma, which is approximately 0.57712. Next, mathematical cyclops. Leonardo Euler was called mathematical cyclops by the fact that his right eye was blind, and later on his left side was being discovered to have a catarata. Yes, he contributed a lot in mathematics by a single eye, and he do it by a single eye. Next, this is a visual or a picture of a cyclops. They can be seen in fictional movies, right? Mathematical notation. Mathematical notation created and popularized by Euler. First, we have the e, the base of the natural logarithm, the constant equal or approximately equal to 2.71828. Next, we also have the small letter I, also known as the imaginary unit, is equal to square root of -1. We also have this f of x, the function of f as applied to the variable of an argument x. We also have this big Greek letter E, also known as sigma, the sum or the total set of numbers. We also have this a, b, c, x, y, z as these are alphabets, but in mathematics they consider as symbols or variables. So A, B, C are constant, such as the sides of a triangle. Yes, we all know that triangle's formula is C equals to A squared plus B squared. Next, we also have this X, Y, Z. They are variables of unknown in an equation. Um, this X, Y, Z can be considered as a variable. Pero, pwede naman tayo gumamit ng other variable except X, Y, Z kasi everyone or ginagamit lang natin sila as a representation. Next, we also have this trigonometric function for sine, cosine, tangent, cotangent, secant, and cosecant. Next or last, we have the pi, the ratio of circle circumference to its diameter. There are Euler's contribution, birth of calculus. Number theory. Euler's interest in number theory can be traced in the influence of Christian Goldbach. Christian Goldbach, he's a friend of Euler in St. Petersburg in Russia. Next, most of his work is based on periodic Fermat ideas. Totoo yan kasi lahat ng gawa ni Euler ay may connection kay periodic Fermat ideas kasi si periodic Fermat ay maraming mga unpublished at hindi natapos na mga formula dahil nga namatay siya or hindi na kaya. So, ginawa ni Euler, tinugulungan niya, dinevelop niya, inimprove niya ito at nagkaroon pa ng bagong formula or ginawa niya ito para matapos iyon. Next, we have the Euler pi function and Euler theorem. Euler pi function, gusto lang itong sabihin na yung pi of p is equals to p minus 1. Na kung saan itong Euler pi function, meron siyang connection dun sa Euler theorem na kung saan hahanapin natin yung x and y is equals to dx over dy. Graph theory and topology. The problem is to decide whether each bridge is exactly possible to follow once and return to the starting point. As you can see, we have picture over there na nagpapakita ng map of Coningburg or yung well-known problem na 7 bridges of Coningburg na kung saan gusto nilang masolusyonan kung maaari bang magsumula ka dito sa starting point na to at magwawakas ka doon sa starting point mo noon. Yan ay binigyan solusyon ni Euler at pinakita niya na hindi maaari dahil walang Euler circuit. Dahil doon, ito yung first theorem na kinonsidera bilang part ng graph theory, specifically in planar graph.
Good morning everyone. I'm Dulce Maria Zuniga, presenting the Euler's contribution to calculus. Euler's formula. Euler's formula aided the two important mathematical theory of Leonhard Euler. The first is topological invariance. Topological invariance relating the number of faces, vertices, and edges of any polyhedron. It is written as f plus b minus a is equal to 2, where f is the number of faces, v the number of vertices, and e the number of edges. If a polyhedron is having a number of faces as f, the number of v as vertices, and the number of e as edges, then the relationship of f plus v minus a is equal to 2 is known as Euler's formula. Topological invariance. Topological invariance relating the number of faces, vertices, and edges of any polyhedron. In geometry, polyhedron or polyhedra is a three-dimensional shape with a flat polygonal face, straight edge, and sharp corner or vertices. The word polyhedrons come from the Greek word poly means stem of many, hadrons, form of base or seat. Euler's polyhedral formula, one of the first discoveries in topology, comes second only to the Euler's identity for mathematical beauty. The formula applies to convex polyhedrons which are shaped with straight edges and flat faces. Euler's formula only works for polyhedral that follows certain rules. The rules in this formula is The shape must not have a holes and that must not intersect with itself. These are the example of polyhedron shape with a flat face. In the upper part, there is a tetrahedron with a 4 faces, 4 verticals, and 6 edges. The next is triangular prism with 5 faces, 6 vertices, and 9 edges. The next is the dodecahedron with a 12 faces, 20 vertices, and 30 edges. In the lower part, there is cube with a 6 faces, 8 verticals, and 12 edges. The next is the icosahedron with 20 faces, 12 vertices, and 30 edges. The next is cuboid with 6 faces, 8 vertices, and 12 edges. These are only the example of polyhedron shape. Solve a problem about topological invariance. Using Euler's formula, find the vertices, edges, and face of a cube. Using the formula of f plus v minus e. The cube has 6 faces, 8 vertices, and 12 edges. F plus v minus e is equal to 6 plus 8 minus 12. The product of this is 2. Let's solve the next problem. Using again the Euler's formula for the dodecahedron with a given faces of 8, vertices of 6, and edge of 12. In the given problem, the f, the e, and the v is given, where the f is equivalent to 8, the v is equal to 6, and the e is equal to 12. The formula is f plus v minus e is equal to 8 plus 6 minus 12 is equal to 2. As you observe in the 2 problem, you will see that the product that we will get is always 2. Because when you add the faces and vertices and minus the edges of any polyhedron shapes with a flat faces, you always get the product of 2. Euler's identity. Euler's identity is an equality found in mathematics that has been compared to a Shakespearean sonnet and described as the most beautiful equation. Euler's identity used to show the constant e, I, and pi are related to each other. Euler's identity is the most beautiful equation in mathematics because in one equation, there is a 5 constant and 3 mathematical operation. This 5 constant is 0, 1, I, pi, and e. And these 3 mathematical operations that used in the formula is exponentation, addition, and multiplication. Euler's identity is equal to e raised to I pi plus 1 equal to 0, where e is called the Euler's number. Euler's number is approximately 2.7182. Euler's number is irrational number because it is not repeating and not terminating decimal. I is called the imaginary unit. Imaginary unit represent the square root of -1, and pi is the circumference of the circle divided by diameter. Pi is approximately 3.14, and pi is also irrational number because it is not terminating and not repeating decimal. Here is a video that will show the history of Euler's identity.
Today, we will discuss about the birth of calculus by Pierre Fermat. So, who is Pierre Fermat? Fermat is born and raised in Beaumont-de-Lomagne, and he is a French mathematician who is often called the founder of the modern theory of numbers. Together with René Descartes, Fermat was one of the 2 leading mathematicians of the first half of the 17th century. He is also a lawyer, and for the remainder of his life, he lived in Toulouse, but as well as working there, he also worked in his hometown of Beaumont Delaunay. Fermat's real love in mathematics. Fermat was born in August 17, 1601 in Beaumont Delaunay, France, and his death was in January 12, 1665 in Castres, France. So, what are these topics? First, the Fermat contributions. Second, his invention of analytic geometry. Third, the Diophantus Arithmetica. Let's proceed of Fermat contributions. The first contribution is calculus. The creators of calculus, including Fermat, relied on geometric and physical, mostly kinematical and dynamical institutions to get them ahead. They looked at what passed in their imaginations for the graph of a continuous curve. Fermat contributed to the development of the calculus through his work on the properties of curves. He found the areas bounded by these curves, though a summation process. We call now this as a process of integral calculus. It is ironic that Fermat did not see what we now call the fundamental theorem of calculus. However, his work on this subject was an aid to developing the differential calculus. Next contribution is the law of refraction. Fermat showed that the law of refraction is consistent with the principle of least time. From these principles, Fermat deduced the familiar laws of reflection and refraction. The angle of reflection, the sine of the angle of incidence, is a constant number times the sine of the angle of refraction in passing from one medium to another. Fermat had a disagreement with the philosopher and amateur mathematician René Descartes about the reflection and refraction. So Descartes was trying to justify the sine law or Snell's law by saying that light travels more rapidly in the denser of two media involved in refraction. So 20 years later, Fermat realized that this appeared to be in conflict with the Aristotelian view that nature always chooses the shortest path. Third contribution was the law of interaction. Fermat applied his method of maxima and minima. So he made the assumption that light travels less rapidly in the medium, and he showed that the law of refraction is consistent with the principle of least time. Also from this principle, Fermat deduced the familiar laws of reflection and refraction. And the angle of reflection, the sine of the angle of incidence, is a constant number times the sine of the angle of refraction in passing from one medium to another. Here are the other contributions that we'll discuss later. Let's move on his invention of analytic geometry. Analytic geometry, also called coordinate geometry, Cartesian geometry, is a mathematical subject in which algebraic symbolism and methods are used to represent and solve problems in geometry. The importance of analytic geometry is that it establishes a correspondence between geometric curves and algebraic equations. This correspondence makes it possible to reformulate problems in geometry as equivalent problems in algebra, and vice versa also. The methods of either subject can then be used to solve problems in the other. So The French mathematician Francois Viet introduced the first systematic algebraic notation, using letters to represent known and unknown numerical quantities. Is Fermat emphasized that any relation between x and y coordinates determines a curve. This means that, using this idea, he recast Apollonius. Fermat indicates that any quadratic equation in x and y can be put into the standard form of one of the conic sections. Fermat had set down a theory of what we should now call analytic geometry, almost identical with what René Descartes had developed in his La Géométrie in 1637. Were done in his invention of analytic geometry, so let's proceed on his Diophantus Arithmetica. Did you know that Arithmetica is the major work of Diophantus and the most prominent work on algebra in Greek mathematics? It is a collection of problems giving numerical solutions of both determinate and indeterminate equations. Of the original 13 books, of which Arithmetica consists only 6 have survived. So, sinasabi dito na uh, yung meron Arithmetica na 13 books, kaso 6 lang ang nag-survive. Pero, there are some who believe that 4 Arabic books discovered in 1968 are also by Diophantus. So, some Diopantine problems from Arithmetica have been found in Arabic sources.
Moving on the topic that Pierre de Fermat was developed is what we call Fermat prime. First, what is prime? Prime is a whole number greater than 1 that cannot be made by multiplying other whole numbers. For example, the number 5, 7, and 11. Why 5 is considered as a prime number? Because you cannot multiply two whole numbers together to make 5. For example, you cannot multiply 2 and 3 together to make 5, unless the number 1. So, according to Pierre de Fermat, the form 2 raised to 2 raised to n plus 1 is a prime number for some positive integer n, and take note of this that according to him, it's not greater than 4. For example, 2 raised to 2 raised to 3 plus 1. 3 is not greater than 4, and it is equals to 2 raised to 8 plus 1, and the answer will be 257. As you can see, the answer is considered as a prime number because there is no two whole numbers together multiplying to get 257. And his basis on his knowledge that numbers of this form are prime for values of n from 1 to 4. And the French mathematician Pierre de Fermat conjectured that all numbers of this form are prime. Next, focus on this one. According to the Swiss mathematician Leonhard Euler, showed that Fermat's conjecture is false. For him, he used greater than 4, which is number 5. But according to Pierre de Fermat, it's not greater than 4. For example, 2 squared raised to 5 plus 1 is equals to 2 raised to 32 plus 1. The answer will be 4,294,967,217. But it is divisible by 641. So it is a composite number, it's not a prime number, and a special type of composite number known as the pseudo-prime. So in fact, it is known that numbers of this form are not prime from 5 to 30. So until now, it's placing doubt on the existence of any Fermat primes for values of n is greater than 4. Again, according to Pierre de Fermat, it's not greater than 4, but according to him, the number from 5 to 30 is considered as a prime number. But according to Leonhard Euler, he showed that Fermat's conjecture is false because he tried the number 5 which is greater than 4, and he proves that it is divisible by 641, so therefore it's not a prime number but it is a composite number. Moving on, Fermat's first and last theorem, but before I will discuss it, I will tell you some trivia. Did you know that when we call theorem, it is a study and has a evidence but not 100% proven? When a study is 100% proven, we call it postulates. So here is the Fermat's theorem, or also known as Fermat's Lille theorem and Fermat's primality test. Here it says that for any prime number p and any integer a such that p does not divide a. So p divides exactly in a raised to p minus a. So this is also one of the definition of a prime number. And although a number n does not divide exactly into a raised to n minus a, for some a must be a composite number. Again, when we say a composite number, there are two whole numbers or more than two whole numbers together to make any integer. But the converse is not necessarily true, because numbers are starting 1, 2, 3, 4, 5, so on and so forth. So, not all numbers are considered as a prime number. For example, let a is equals to 2 and n is equals to 341. A raised to n minus a is equals to 2 raised to 341 minus 2. Look at this one. 341 is used, but this number is not a prime number because it is divisible by 11. This is a composite number called pseudoprime. The picture below is just like this, but it's about calculating Fermat's theorem using a calculator. So, Fermat's theorem gives a test that is necessary but not sufficient for primality. So, this is the last that Fermat developed, which we call Fermat's last theorem, or also known as Fermat's greatest theory. So, according to him, Arithmetica by Diophantus of Alexandria. By the way, Diophantus is Fermat's friend, and he states that it is impossible for a cube to be a sum of two cubes, a fourth power to be a sum of two fourth powers, or in general, for any number that is a power greater than the second to be the sum of two like powers. He says that I have discovered a truly remarkable proof, which is the Fermat's last theorem, but this margin is too small to contain it. So, this statement says that there are no natural numbers in which n is a natural number greater than 2. For example, if n is equals to 3, then x cubed plus y cubed is equals to z cubed. And 4 centuries mathematicians were baffled by this statement, for no one could prove or disprove Fermat's last theorem. So there is an English mathematician who had been interested in the theorem since the age of 10, and he is Andrew Wiles. Andrew Wiles presented a proof of the Shimura-Taniyama-Will conjecture in 1993. So, what is Shimura-Taniyama-Will conjecture? For example, Fermat himself did a proof of another theorem that effectively solved the case for n is equals to 4. And by 1993, with the help of computers, it was confirmed for all prime numbers n is less than 4 million, and by that time, mathematicians has discovered that proving a special case of a result from algebraic geometry and number theory known as the Shimura-Taniyama-Will conjecture would be equivalent to proving Fermat's last theorem. But there's an error was found in this proof. However, but with the help from his former student, who is Richard Taylor, and Wiles finally devised a proof of Fermat's last theorem, which was published in 1995 in the journal Annals of Mathematics. So that centuries had passed without a proof that led and many mathematicians to suspect that Fermat has mistaken in thinking he actually had a proof.
Hi everyone, I, Kenneth Betagco, together with Maria Erica Lingat, are going to discuss René Descartes and his contribution on the birth of calculus.
This will going to be the flow of our discussion. First, what is calculus? We are going to explain first what is the definition of calculus. Second, we are also going to briefly introduce who is René Descartes. And lastly, we are going to focus and discuss on his contributions on calculus.
But before we proceed on René Descartes, let's have discuss calculus first. So what is calculus? Calculus, originally called infinitesimal calculus or the calculus of infinitesimal. So calculus is a branch of mathematics that involve study of rate and change. Calculus was developed in late 17th century by two mathematicians. First, Gottfried Leibniz, second, Isaac Newton. Isaac Newton developed first the calculus and applied it directly to the understanding of physical system. Independently, Leibniz developed notation uses in calculus, put simply, while basic math uses operations such as plus, minus, times, and divide. Calculus uses operations that employ function and integral to calculate rate and change. René Descartes said that it is not enough to have a good mind. The main thing is to use it well. My explanation about that is, it is not enough to have a good thinking or smart thinking. The important thing is you should use it correctly in the right way. René Descartes was born March 31, 1596 in Turin, France, and at the age of 54, René Descartes was died February 1650, and he contracted pneumonia. At the age of 9, René Descartes was sent to the Jesuit College of La Fleche in Anjou, and this is where his skills and thoughts were shaped. Anjou was a French province straddling in the lower Loire of river. So it is a capital of Angers. So René Descartes studied physics and metaphysics, moral philosophy, logic, classical geometry, modern algebra, and literature. Out of all this, Descartes was only found mathematics is to be satisfactory in reaching of the science of nature. So when we say satisfactory, it is a fulfilling of expectation or needs. La Geometrie 1637. His only mathematical work include with his published Discourse on Method. So Discourse on Method is Descartes' attempt to explain on his method through even the most difficult of problems. So he illustrate the development of his method through brief autobiographical sketch, interpers, and philosophical arguments. He allowed the development of Newton and Leibniz discoveries, and this is where he presented his invention, the analytic geometry. Some examples of analytic geometry is ellipse and circle. They under for analytic geometry because, as what was said a while ago, we can make curves and geometrical shape from algebraic equation. Cartesian coordinate system, or other term Cartesian plane or number of plane. It is a system he devised for plotting points to form lines or curve represented by equations. So Cartesian plane is sometimes referred to as a x and y plane or coordinate plane. The horizontal line here is referred to x-axis, while the vertical line is known for y-axis. An easy way to remember the order of operation is that you read to left to right. And so the first line is horizontal line or the x-axis, which also comes first alphabetically. Standard algebraic notation is using of letter or variable to represent known and unknown quantities. In algebra, we use letter to represent number, and these are usually letters. The symbols are called variables. Using symbols instead of number is great because they may sometimes represent long numbers. And so, it's safe that having the right amount every time, like pi, which is 3.1415, and so on, which make calculating much easier instead of writing a whole number. Let's give examples. Instead of writing multiplication sign, we can remove it and just write AB instead of A times V. Another example. Instead of division sign in algebra, we use fraction to divide number or variable.
Hello everyone, my name is Maria Erica Silingat. One of my groupmate, Kenneth Bitagcool, already presented some information about René Descartes and his contributions on the birth of calculus, and here is the continuation. Descartes believed that mathematics was the only thing that is certain or true. In this quote, it was mentioned that mathematics is the only thing that is certain or true for him. Therefore, he believed that everything can be reasoned with mathematics. And probably this is the reason why Descartes continued working in mathematics. So before anything else, let's first learn who is René Descartes. I think anyone who studied philosophy in their high school will know that René Descartes is a French philosopher entitled Father of Modern Philosophy. The reason why he is called like that is because he did not base his ideas from his own feelings, emotions, and other past studies. Rather, he created a solid foundation of new knowledge as he extends mathematical methods to science and philosophy. Which means that we can find a clear reasoning. The clear reasoning are the mathematical methods with all the knowledge we have from science and philosophy. And soon enough, these provided encouragements and new ideas for philosophies and philosophers. Next, he was also called the father of analytical geometry, as he is the one who discovered analytic geometry. This is going to be further explained on the next slides. Additionally, he is also a French philosopher, as what I've said a while ago, and a mathematician who has a big contribution on math. Here comes where he started to be interested in mathematics. On November 1618, while he was a volunteered army after he graduated, he saw Isaac Bigman, which is a prominent mathematician, together with other people gathering on a posted notice. As he is having difficulties in understanding and reading it, he then asked Bigman for a translation. After that, he now knew that the notice is a mathematical problem. He accepted the challenge of attempting to solve it, and after a few minutes, he gave the correct answer to Bigman. For the next word, Isaac Bigman. He was included here as he played a significant role in the life of Descartes, as he became the mentor of Descartes and after that event where Descartes said the right answer on the math problem. From then on, he is the one who always gave encouragement to Descartes, and this allowed his skills in math to be used, which led him to be interested in theoretical problems. After learning some facts about Descartes, let's now discuss Descartes' contribution on the birth of calculus. Analytic geometry is the main topic written under his work La Geometrie. Its other terms are coordinate geometry, Cartesian geometry, geometrical calculus, or calculus with analytic geometry. It was on March 1619 where Descartes realized that a pair of numbers, x and y, can be plotted on the horizontal and vertical axis, or what we call a Cartesian plane. This subtopic will be explained later in the succeeding slides. In here, it was said to be that analytic geometry is the union or relation between algebra and geometry, where we can graph points and create curves, lines, and circles with the help of the algebraic equations. Also, algebraic equations can be modified from curves, lines, and points. Here are some of the examples of analytic geometry, the parabola and hyperbola. As we know, in this given example, we can find the equation of a curve by looking at its graph and vice versa. Their equation and graphs are connected to one another. Cartesian plane. I know most of us are familiar with this, and it consists of 4 quadrants, as can be seen in the presentation, consisting pairs of integers per quadrant. A Cartesian plane only has one origin, which is the center of the plane, and this can be found in the intersection of the two lines. The horizontal line represents the x-axis, while the vertical line represents the y-axis. Next, Renatus Cartesius. This is Descartes' Latin name, and this is where his discovered Cartesian plane derived from. Cartesius, Cartesian. Next is the Descartes rule of signs. To find real roots, we should always consider the number of sign changes. But first, we need to learn that there are two kinds of real roots, which are the positive real roots and negative real roots. And this Descartes rule of signs stated that the number of positive real roots is equal to the changes in sign in f of x, while in negative real roots, the number of changes in sign in f of negative x. As we can see on the slide, in getting the f of x of a function, we just need to retain it, while in f of negative x, we need to change the signs by distributing the negative signs on all of the x in the function. The f of x and f of negative x is already presented here in the slide. So after doing so, let's now proceed in finding the real roots or real zeros in the given function. For the f of x, we can see that the first term, 3x cubed, is positive, and the second term, negative 4x cubed, is negative. That means one change because the change in the sign is evident, from positive to negative. Let's observe the second and third terms. The sign did not change as they are still both negative, so it means there is no change or zero change. For the third and fourth terms, the third term is negative while the fourth term is positive, and that means one change. So all in all, there is a total of 2 changes for the function f of x. But it doesn't stop there, as it was also stated that we should always deduct 2 or an even number on the changes of signs until we can get an answer of 0 or 1, because these are the considered minimum number of real roots in the given function. 2 minus 2 is 0. Therefore, the possible positive real roots for this function are 2 and 0. Let's now proceed on the negative function. The only changes in sign that we can see is in the second and third term. So, there is only one negative real roots in this function. Therefore, the possible number of positive real roots in this function are 2 and 0, while the number of negative real roots in here is guaranteed to be 1. Here are the sources.